Gregório Couto Faria, obtained his master's degree in applied physics from the San Carlos Institute of Physics in 28. Then he obtained his doctorate in 2011 in a dual diploma agreement between the University of São Paulo and the Technischen Universität Darmstadt, Germany. On the German side, Gregório is Doctor Summa Cum Laude, the highest distinction awarded by the German graduate model. He did a postdoc also at Technischen University Darmstadt, working on the elucidation of charge transport processes in luminescent and photovoltaic polymer science system. Between 2014 and 2016, he made his second postdoctoral degree at Stanford University, where he worked with mixed conductor applied to artificial intelligence. Since 2013, he is a professor at the San Carlos Institute of Physics. Today, he will talk about ballet of ion and electrons, fundamental and application of organic mixed conductor. Please.
Thank you so much, Vicente, for the nice introduction. I think everyone is listening to you well. I think so, right? The volume is okay. First of all, I would like to thank Vicente and Rogério and everyone in the Institute for the invitation, for the kind invitation to be here presenting a little bit of what we've been doing the last about 3 years. Is actually, I really like Instituto de Física Teórica because back in my undergrad around 2003, 2004, I actually came here for 2 cosmological school and was actually held in Pamplona Street, very historical building. I used to love that part of the city and as well as the building. And it's the first time that I come to the new campus of IFT, so it's actually a very nice day for me. So thank you very much. So as Vicente have introduced, I'm going to talk a little bit about some experimental results. So we are going to change a little bit of mood from theoretical to a little bit of experiments. But I'm going to show you how important is also for us to model and understand fundamentals of physical and chemistry of those materials in order to propose creative and impactful application. So, okay, so let's get started. The title of my presentation has to do with, let me see, where is my pointer? It's right here. So it has to do with mixed conductors. So the first question is, what is mixed conductors? So mixed conductors is basically materials that are able to efficiently conduct electrons and ions at similar efficiency. And the idea of being organic is because they are made out of polymers. So you can have inorganic materials that are also able to have this sort of mixed conductivity, but polymers have some advantages that I'm going to try to convince you about it in the following slides. And why we need mixed conductors. So first of all, electronic conductivity is very important because this is basically the technology that the mankind actually dominates. So we have all these integrated circuits where we do computation, where we actually communicate with flux of electrons. So this we dominate well. As for ionic conductivity, we have to remember that all biological all biological systems, they actually do communicate using ion flux. So we are all, very intricate machines that do communicate through flux of ions. This is basically how your neurons is right now firing. This is how our cardiac cells are actually, pumping blood, is almost through some sort of ionic channel that actually opens and closes. So in order not only to interface biology, but also to mimic biology, because there is a bunch of applications that I'm going to show you in the next slide, it's very important to have a transducer, which is basically a translator between how biology do communicate to the way we actually sense electronic and do technology. So that's the reason we want mixed conductor, to sort of bridge these 2 different worlds, okay? But you can think about, okay, so I understand why we need mixed conductors, but why polymer materials? Because initially polymer, if you think about polymer, we have a lot of polymeric material around us, and all those materials have some sort of insulating properties, and this is not very good electronic conductor, right? So they even actually have been used for centuries to actually coat copper wire in order to insulate electricity. So why we need this? In fact, most of the, I think the battery is not going well here. Okay. So many of the polymers, the aliphatic polymers, they are indeed insulating, but we have a class of polymeric materials known as conjugated polymers that basically have, alternation of single and double bonds that actually have semiconducting properties. And with these materials, we can do a lot of technology, as I'm going to show you in the next few slides. Just a very brief overview. I think all of us know about this, but just so we pick and distinct the different materials. So we can have conductors, and if you think about your high school chemistry, you remember about the valence band and the conduction band. And for conductors, you either have one of the bands. Here we have the valence band half-filled. So you have free states on the valence band, and therefore charges can actually easily or almost free of energy can hope to new or empty space. Let me see.
Also that.
Okay, so let's try this real quick. There we go. So here's the laser, and yeah, there we go. Thank you so much, Rogério. So we have, a half-filled band where, electrons can move, or the band can be actually completely filled, but then the energy gap between the valence and the conduction band is actually very small. And then by some sort of small thermal fluctuation of either infrared emission, you can actually promote electrons and get high conductivity. So this is the conductors. Insulating or insulator materials are those that are actually the valence band is completely filled, and the energy gap between the valence and the conduction band is very high, normally higher than 3, 4 electron volts, and therefore is very unlikely to find an electron actually on the conduction band, and therefore conductivity is rather small. For a semiconductor, you have something in between. So you have a filled valence band, but the energy gap is actually narrower. So it's in between 1, 0.8, all the way to 3 electron volts, which is basically the visible range. So with natural radiation that actually permeate us, we can easily pick electrons from the valence band and promote it to the conduction band and do some sort of electronics with it, okay? So this is the basic differentiation between all these materials. And how actually those bands actually come together, right? So this is a basic molecular model theory, and this is very simple to understand how we can actually, from bringing two atoms together, we can form different bands. So think about of having, two hydrogen atoms. They are actually far apart. So they have one electron, so they have the wave function, right? And as you bring them close together, those wave functions will interfere. So they can interfere in a way that is constructive and in a way that is destructive, right? Because of the sign of the wave function. And if you think about the square of this wavelength, which gives you the probability, so the constructive interference actually brings or have a very high probability of electrons to be in between the atoms, whereas the destructive one has actually almost zero probability of having electrons between those atoms. Those two orbitals are actually different, so they bring different energy. And here's a little experiment showing the density of electrons. In the constructive one, you see a high probability here, which is not the case for the destructive one. And therefore, two wavelengths or two waveforms that are actually at the same energy, when they bring them together, they form two different states that are actually separated by a gap of energy. And in this case, for a more complicated, which is the conjugated polymers that we are going to talk about, this gap of energy is about 1 to 3, right? So all those materials that have alternating single and double bonds, they actually give you semiconducting properties.
So what is plus and minus?
Plus and minus here?
Is it electric charge?
Is just the sign of the wave, the wave function, because they can be symmetric or asymmetric, right? So this is the probability of when you actually sum them up. So you have to normalize so they can plus or minus. So this is the two ways you can add up two wave.
You have 2 electrons.
Exactly, 2 electrons. So these are 2 atoms, hydrogen atoms that are far apart. So you bring them close together, and then you are just evaluating how the waveform of those electrons actually do behave. And they behave in a way that they break the degeneracy, or they are equal energy, and therefore they become 2 different energy and creating this band gap.
In one case, you can form a hydrogen molecule, the other one you cannot.
Yeah, so actually you have these 2 working together. So this is the bounding molecular orbital, and this is the anti-bounding molecular orbital. They all actually exist in terms of energy states of the molecule, but of course, the electrons populate the one that actually is the lower energy state. And if you want to play with these electrons, you actually have to promote one of them to the highest energy, and therefore you can have some sort of conductivity. And you have to be careful. Well, this is the bounding molecular orbital is the one that actually holds the molecule. So if you shine a lot of lights or high intensity radiation, you can actually promote these 2 electrons, and then you can break the molecule apart. So this is one of the problems we face with polymers, because if you shine a lot of radiation, you can actually break this conjugation and, of course, break the polymer.
Psi minus will break the molecule?
Yeah, because the probability of electrons to be in between the 2 atoms are small, and therefore, if all the electrons are there, they are actually not holding the cohesive of the molecule together. So you have to be careful how much intensity of radiation you actually shine on your molecule, because they can break it apart. This is a simple model for hydrogen, but just to give you an idea of how this, valence band and conduction band actually start popping when you bring molecules or atoms together to form a molecule, right? But these are discrete states, so
You can solve this exactly, right?
yeah. For hydrogen is easy, and even for yeah, exactly. And of course, for polymers, we don't have hydrogen. We have a more complicated molecule, which is carbon. And of course, this is for single bonds. Here we have double bonds, so you have sigma and p orbitals as well. We have more complicated structure. But yes, you can. And you see hybridization. You see a lot of different things that we heard about in high school chemistry, and etc. But just to give a big picture on how those states actually appears when you form that molecule, this is more or less the big picture of it. And but those are discrete states. So if you would have transition between these 2 states, they are very narrow. But we know that polymers are amorphous materials. Those transitions are far from being very narrow. And actually, we don't call these states, we call these bands. And the way you form a band is because, a polymer is a lot of similar monomers, which is basically the same monomer, which is the same repetition unit that actually repeats several times in order to form a very long chain. And this very long chain, they can actually twist, they can kink, they actually experiment different chemical environments, and therefore all that state that were actually very defined in energy become blurry, band transition where you have very broad transition going on, okay? And here is several examples of these materials. You can easily synthesize those materials with, different synthesis routes, and you can actually pick different molecules, structures, and atoms to actually, tune that band gap, tune crystallinity, tune a lot of the material properties. So that's the reason this is a vast field of research for chemistry as well. But okay, so
Sorry.
yeah, go ahead.
To get the band structure in this more complicated case, you need to solve some very complicated Schrödinger equation.
Yeah, so then you have to solve, you have to use ab initio or even, more complicated theoretical framework to sort of, because now we are no longer talking about two single atoms, right? We are talking about, maybe 1,000 of atoms, in the same molecule chain.
You get the simple structure of two bands and like.
Exactly, then you get that. What we call HOMO and LUMO, which is highest occupied molecular orbital and lowest unoccupied molecular orbital, which is basically the conduction and valence band. But yes, there is a lot of chemistry and theoretical physicists doing those kind of calculation. Marília Caldas, for instance, at the FUSP here, she actually collaborates with us, and she has published recently a Advanced Science, I guess, doing calculations on materials like that are used for OPV, which is organic photovoltaics. So it's very important because for organic photovoltaic, you want to have a band gap that actually emits the solar radiation, right? Because otherwise you're going to be absorbing outside of the solar spectrum, and therefore your efficiency will go down. So in order to, tell the chemistry, do that kind of molecule, you have to do screening calculation, not to lose a lot of time in the lab. So it's very important to do this kind of calculation. Okay, so, it's a lot of backgrounds, but we want to see conduction going on. So the very first device that actually was proposed using these materials, and actually is the reason organic electronics actually took off, is what we call organic light-emitting diodes. So it's basically a device, like a diode, that actually shine light, okay? And the way you do it is actually fairly simple. So you use a substrate. It could be a glass. It could be a PET substrate if you want to make it flexible. Then you put a coat of semi-transparent electrode. This is the ITO, indium thin oxide. It's just an oxide. It's transparent. It's very high conductive. And you need that because you have to apply a potential between the film. And then you actually put your light-emitting polymer, one of those conjugated polymers. You deposit it on the top of this structure, and you finalize the device structure by evaporating a metal electrode. So now you have what we call a sandwich type of device, where two electrodes kind of sandwich in between a polymer layer. And the way this device works is quite simple. Of course, the ITO or the oxide, the transparent oxide and the metal electrode, you have to pick properly. You want to pick a work function of one of these materials, metals or oxide, to be actually matching the valence band and the conduction band of your material, because otherwise you're going to have to give energy for those materials to be injected or removed from the material. So here is the anode, which is basically the ITO, the oxide. So here's the work function, and this is basically the valence band. And the way it works, when you apply a potential between your anode and cathode, the cathode is basically the metal electrode, holes, or basically, the vacancy of an electron is injected into the valence band. You can think about an electron being extracted from the valence band by that particular metal. And in the opposite electrode, an electron is injected into the conduction band. And those two charges are actually conducted through these two bands, conduction and valence band. And at some point, they can meet each other. So you have an electron and a vacancy of electron. Of course, that electron we will want to relax on that vacancy. So they basically, relax back to that vacancy on the valence band. And for that, it has to release some energy, and releases that energy shining some light, right? And, basically because you can pick, that difference of energy between the band gap and the valence band being on the visible light, you can have a spectrum that actually emits on, on colors that we are common, or we know as a visible light. And I have here a device just to demonstrate to you that we built on our lab. It's a very simple demonstration. This is a polymer light-emitting diode, very similar to this one. And we just put a small little hardware where it mimics a dice. So it's actually 2 dice. So as I shake it, it gives me 1 or 6. And then I shake it again, 5 and 1, and so on and so forth. And of course, this is very thick because I have the hardware, I have the hardware, I have the battery. But I'm not sure if you can see it, but the display is simple as this. And the highest thickness that you see on the display is basically the glass substrate, because the polymer film is about 80 nanometers. So 80 nanometer is very, very thin. So you can make very, very thin electronics. And if you want to pick, instead of glass substrate, you want to pick, for instance, a flexible substrate, you can make this flexible because polymers are flexible. So I'm going to pass along if you want to just see it, the thickness, and play a little bit. This is a yellow material, so shines on yellow color, but we have all type of colors. And actually, those kind of application is already in the market. So this is a LG TV that I accessed yesterday. So if you have about 27,000 Brazilian reais, you can buy one of these and put on your wall, because basically the hardware sits on a separate device, and simply because the LED or the display is so thin that is actually thinner than a paper announcement like that. So you can stick on your wall, and the hardware has to be placed elsewhere. But it's still very expensive. But this is the way technology develops. At some point, LCD is still very competitive, but at some point this price will drop, and eventually all of us will have this very thin, lightweight, and flexible, efficient polymeric TVs and displays on our offices and living rooms.
So there's no batteries here, right?
Yeah, there is a...
You need a battery.
Yeah, we do, yeah. But actually, this is important. As opposed to the normal LCD display, you have to have a back illumination, what we call back panel, that actually illuminates throughout all the TV or all the size of your display. And then the LCD simply kind of selects the wavelength you want to see on that particular pixel. But say that you have half of your screen black. It means that the LCD is simply blocking all the radiation, but before the LCD, all the radiation is being generated. So you have a lot of power consumption and waste of energy being blocked. And this is no longer the case for those materials, because if you want to have a black spot, you simply turn off that particular pixel. So they are actually way more efficient than LCD. So eventually, this will take over the market of LCD and hopefully help as well. One of the biggest problems in mankind, which is the energy problem. I think it's one of the... so this is just, yeah, please.
Just a quick question about
Yeah.
mechanisms.
Sure.
So do you have an exciton formation before recombination?
Exactly, yeah. The exciton formation normally is the opposite, when you absorb lights and then you create a pair, right? And it's basically the opposite. But yes, at some point, a electron finds a hole, they bind together, and they recombine. So you have an exciton and a recombination of that exciton.
But do you need the exciton, or is it just because of the material typically forms an
Yeah, the material always forms an exciton because of the type of exciton. It's a Vanier exciton, so they are very bind, so then they recombine. And you can think about why people are looking into, why people are looking into organic photovoltaics, because photovoltaics is basically the opposite of it, right? Here I'm applying a voltage to inject charges to create light. But what I could do, I could shine light to create charges, then I create an exciton, and then I have to choose different molecules, because now I don't want the exciton to be recombined. I want two exons to be breaked apart, and then I actually push those charges to my contacts, and therefore I have energy created by light absorption. So it goes both ways. The structure is pretty much the same for a LED or organic light emitting diodes, or a photovoltaic as well. But since I was on the theoretical physics department or institute, I picked one interesting work that actually deals with interface problems that might be interesting to the audience. We can do all this kind of devices and technology that are actually very important, but polymers are basically hydrocarbonate material as we are. And we actually get old because we simply oxidize. The oxygen that actually keeps us alive in the short to medium term actually kills us in the long term, because you basically oxide, and all this, signs of being old is basically due to free radicals that you have on your body created by all this oxygen. You can actually easily see this happening when you basically watch an interview of a marathon runner. So he has, 25 years old, and he looks like he's 40. And the reason that happens is because when he trains, he actually consumes a lot of oxygen, and therefore he's more, propense to be oxidized. And this happens to polymers because, it's pretty much carbon and hydrogen as well. So polymers also suffer with the presence of oxygen. And basically what happens is that the oxygen traps electrons, and all those important electrons that are used to either shine light or to create light are actually captured by that oxygen and creates a big trouble for that technology. So we actually did a very interesting work that actually generated 3 papers, which was very interesting because it was way deeper than we thought. But we took a prototype polymer, which we call P3HT, is a polythiophene. It's a very well-known and used polymer, either on field effect transistor or photovoltaic. And we did some sort of oxygen exposure to see how that oxygen would actually degrade the material. And the way it works, so you have here the backbone or the conjugated chain plus an oxygen. And because of the electron affinity, which is very high, like a fluor and oxygen, they are very electronegative. The oxygen actually sits very close to the conjugated backbone. And by some sort of stimulus, which could be light or even some sort of thermal fluctuation, you generate those pairs of electron and holes. And because you promote a electron to the conduction band, and if you have oxygen around, that oxygen actually can trap or can push that oxygen closer to the oxygen, leaving this hole behind. And this oxygen gets trapped, and of course, because they are trapped, they are no longer, actuating as a conductor. And because of that, you ended up with an oxygen molecule that is negatively charged and a polymer that is positively charged. So you sort of p-dope your polymer with this type of process. So we wanted to look into more details of that process. So what we did, we basically built on our lab a simple, what we call diode, which is glass substrate and transparent oxide, the polymer film, and here a metal electrode, which is in this case silver. Okay, so we hook them together. So you can apply a potential, you can do all this very interesting thing. And here's the band diagram where the HOMO and LUMO is basically, the valence band and the conduction band of the material. And those numbers here are the work function of either ITO and the silver metal, silver metal or silver electrode. And the way we actually measured the electrical property of this film is by simply applying a linear increasing voltage. And the reason we do a linear increasing voltage is because this is basically a capacitor. So you have, an electrode separated by a dielectric. So a capacitor gives a capacitive response, what we call displacement current, which is basically C, which is the capacitance, dV/dt, which is the derivation of voltage in time. So if you don't apply, by applying, a linear increasing voltage, this displacement current is basically constant. So you can clearly separate what is a contribution of the displacement current to what is a contribution of conducting charges that are actually, free to move within your polymer. And this is sometimes very intricate to separate them. And by using this linear increasing voltage is a way that we use, basic physics or electromagnetic physics to kind of separate them apart. So the idea is, okay, if the polymer is neutral, so it's not exposed to oxygen, doesn't see oxygen at all, so the polymer is completely neutral, so there is no charge in the polymer. So when I apply this linear increasing voltage, I would see simply this step current, which would be associated to the capacitive response. And then when I would expose my device to oxygen, I would create those charge transfer defect, and therefore I would p-dope my polymer, and then I would be able to extract those holes that are left behind on my polymer. And then we moved, so we created all these devices with the setup and etc. And then when we moved to our experimental setup, this is the picture of a oscilloscope display. This is unexposed, so here's the time of exposure. So this is completely not exposed, so it's sealed. We do have a very big extraction at the middle of this linear increasing voltage. So this was actually very interesting. We weren't expecting that extraction of charges because the material is not exposed, so it's supposed to be neutral. So where is this charging or charges coming from? And actually what we did, we put a small little camera focused on the screen of that particular oscilloscope, and we let the time of exposure goes on. And this is basically what happened. If the time of exposure through oxygen goes on, you see that you clearly have a transition between two different modes of conductivity. First of all, charges were in the middle, and as time evolves, this charge actually gets reduced. You see that this peak is actually being reduced, and this actually gets increased. So you clearly have extraction from different type of charges going on that particular material. And this was very intriguing for us. So we got back to the drawing board, and we wanted first try to understand why we did see charges in unexposed or non-exposed devices. And afterward, we wanted to understand why we have this transition. So there is two questions going on.
What is the difference between the two figures, the two graphs?
Okay, so what we do a two extraction peak or two extraction linear increasing voltage, one after the other, because by playing with the equipment, I can space them and see how they recover. You see that here is about 1 microsecond or something, and you see that they do recover, but just a little bit. So by spacing these two, as I'm going to show you in a few slides, I can actually see how the relaxation or the restoration of that particular condition happens in the kinetics of it, which is very important and gave us a possibility to study this phenomena even further. But I'm going to show you. That's the reason you have two. But okay, so we got back to the drawing board, and here's the band diagram. And actually, it's quite interesting. So you see that the ITO has a work function of 4.8 electron volts. And for a P3HT that has this conduction and valence band number, if the material is undoped, there is no charge in that material, we have the Fermi level basically sitting in the middle of the band gap because this is completely filled, this is completely empty, and therefore, the Fermi level is lying in the middle of the band gap. So when you actually build this device, you have a huge difference of energy between the work function of one of the electrodes and the Fermi level of your material. And of course, when you study thermodynamics, you know that those kind of abrupt change on energy, they are not the nature doesn't like it at all. So what is going to happen? Somehow they're going to exchange charges or something in order to equalize that interface and have a smoother transition between two different Fermi levels. And I give this example to my student, is the same of having two swimming pools, placed in two different heights. And because you have the walls hold the molecules or the water molecules together. But all of a sudden, if you play God and you bring them together, of course, you're going to have a very unstable situation here. And of course, water from this reservoir will come to this reservoir, and etc., in order to equalize this water level. And this is exactly what is going on this interface. And what happened, instead of this static figure that I've shown you before, the realistic one is like this. So the HOMO of the material is actually tilted at the interface in order to match the work function of ITO. And the way the nature does this is by ITO injecting charges at the interface, creating this reservoir of charges at the interface in order for the equilibrium thermodynamics of those two interfaces to be equalized or to be in equilibrium. Of course, I have a slightly difference between the Fermi level of P3HT, which is 4.1, to the work function of silver, which is 4.3. But this is very small compared to the 0.7 electron volts of the interface of ITO. So you do have a little bit of charges on that particular interface, but not as big as that one. And therefore, that first peak that we saw initially on non-exposed device were actually attributed to the extraction of those reservoir of charge that are lying in the interface in order for, of course, energy equalization at that interface. So this is the reason of non-exposed device. And actually, this is quite important for the field because we all knew that those charges were there. But this is the first time a measurement were capable of accessing that type of charges because you create a charge-image interaction here. So it's very hard to really use techniques to access those charges. And because when you remove those charges, you basically take a system that is in equilibrium and take it out of equilibrium. So of course the system wants to restore equilibrium as fast as possible. So you have to use, fast transient response method to really access those charges. And, one of the papers we actually put out based on this material, based on this work, was proposing a technique to really access, a way of accessing that charge and study that charge. And of course, the other question, we solved the first one, the origin of this first peak. But the second question is why, peak number A, which is the one that actually exists in non-exposed device, is dying in detriment of the burning of a new peak that we call B. And you see that the rate seems to be very similar. One actually decay at the same rate that the other one indeed appear. And we actually measure the rate. So this is the charge density of peak A and peak B. So peak A actually decays, peak B rises, and they have basically, recovery constant or very similar, about 70 minutes, one die and the other recovers. So you can really see that one is dying in detriment of the other. So something is happening when oxygen comes and interacts with the molecule that basically kills this reservoir and creates another type of, conducting charges in the polymer. And basically what is happening is basically very clear. Because when you have, some sort of stimulus, as I mentioned, could be light, could be, some sort of thermal fluctuation, you actually create charges. So you create, as my friend there mentioned, we create excitons, so you create pairs of electron and holes. And they can, recombine, but if there is an electron around, as I just mentioned to you, the electron will capture this electron, will trap, and will actually p-dope my polymer, my P3HT polymer. And by p-doping polymer, basically what I'm doing is actually introducing charges at the HOMO of my material, which is the valence band. And when you actually introduce doping charges on your material, what happened to your Fermi level? The Fermi level actually moves towards your HOMO, moves towards your valence band. And by moving towards the valence band, the gap of energy, here, if the Fermi level moves towards the HOMO because of doping, that gap of energy that was creating that reservoir is actually getting smaller and smaller, and therefore this reservoir gets smaller in terms of charge density, and therefore by doping I get rid of this interfacial reservoir of charge. And this is what happens. So as time exposure goes on, I create more doping charge, and the reservoir gets less charge and less charge. And then I sort of explain that type of behavior that I saw on my screen of my oscilloscope. We did, as I mentioned to you, we could play with the distance of two subsequent linear increasing voltage to capture, kinetics of those, recovery kinetics of those reservoir. We did a lot of calculation as well on this matter. I don't want to go into details on this because I want to move to the next topic. But those generated two very nice papers that actually gave us, or we gave good contribution to, a field of or a vertical in organic electronics that wasn't so explored because of lack of methods to access and study those charges. Okay, so I think basically using not only my small LED that I passed around and this oxygen doping work, I think I have proved to you that yes, polymers are capable of conducting electronic charges, either electron or holes. You can see that happening on front of your eyes. But on my title, I also mentioned ionic conductivity, right? So how about ionic conductivity? And the reason polymers actually conduct ions is very interesting. Polymers are a very porous material. So you can think about polymers as being the sponge of your house. So basically, when you come to the Institute and spend your day here, your sponge at home is actually drying out. So when you get back home, it's actually completely dried and very small and stiff, right? But if you take that sponge and pour some water, what happened to that sponge? It just swells. You incorporate that water and swells. And this exactly happened to your polymer. Polymer, if you take that polymeric film and look into the microscope, what you see is basically a plate of spaghetti. Very long chains that are entangled one on the top of the other, and with a lot of different holes and porous holes where, ideally solvents and therefore ions could penetrate in. So, And so that's what I just mentioned. In ideal environment, ions and therefore solvents can penetrate in and can start interacting with your polymer molecule. And when ions do interact with your polymer, you create doping because ions are charged atoms and charged dope polymers. And therefore, by absorbing ions in that very intricate morphology, you can start doing doping of your material. And why this is interesting? This is interesting because now I start building my transduction or my translator between ionic flux to electronic charges that I can measure in the lab, and ionic fluxes that, not only biology, but a lot of other, systems actually do use to communicate. And the best transducer or the device to translate, this type of signals is the transistor. Transistor is an amplifier by nature. We use to amplify a lot of different things in electronics. So the device of choice to use interfacing biology is what we call organic electrochemical transistor. And a transistor is a very simple device, has 3 electrodes, the drain and source, that defines what we call the transistor channel. And on the top of the channel, you have some sort of electrolyte, which is the media that actually holds your ions, interfaced by a gate electrodes. Therefore, by applying potential to this gate, I can force electrically ions from the electrolyte to move into the organic semiconductor. And this is the way it works. So if I don't have any potential to the gate, I can apply a potential between my drain and source, but no charge is coming into the polymer, and therefore my conduction or my current between the drain and source is basically zero. But when I apply a voltage to my gate, here I'm applying positive, so I'm pushing negative ions into the polymer. And for the same reason, the thermodynamic equilibrium that I mentioned before, if one ion, negative ion, goes into the polymer, it is required to maintain bulk neutrality that my drain or my source inject into the polymer a positive holes, or remove an electron if you want to think about it. It's the same thing. So 2 ions here, 2 charges here. So you see you have a translation between 1 ion going in to 1 charge coming in. And therefore you have a 1-to-1 translator between one and another. And basically this is an electrical chemical reaction that happens. So you have a neutral polymer plus a negative ion plus a hole, which is injected. And then you create a polymer that is positively charged, and that is bind to that particular ion, negative ion. So this is some sort of electrical chemical reaction that is going on because of that interaction between the polymer and the ionic species. And because the ions do penetrate the volume of the material, the capacitance of these electrochemical transistors are huge. We are no longer talking about capacitance that are superficial capacitance or area capacitance. We are talking about volumetric capacitance. We can get with these materials capacitance of units of Faradays. For those who know electronics, knows that 1 Faraday of capacitance is huge. It's very hard to find inorganic materials or other materials that actually gives you, within a 1 centimeter by 1 centimeter area, 1 Faraday of capacitance. So this is huge. And because this capacitance is huge, meaning the ability of uptake ionic species into the polymer is huge, electrical chemical transistor made out of polymers is one of the highest transconductance ever published. Transconductance is basically a translation of the on-off ratio of your transistor. So here we have a series of even 3 and 5 family of inorganic materials made of these transistors. You have transconductance of as high as 1.4 millisiemens, and with all these polymers, we can get up to 4 millisiemens. Actually, those numbers are outdated. In my lab, for instance, we just got 6.5 millisiemens, so it's almost 1.5 highest than the one that actually was ever published. And I know a group from Imperial College that just published one with 30 millisiemens, so it's 5 times best than mine. So, by playing with the condition, you can increase the ability of ion uptake. And why this is important? This is important because I can build what they call impedance biosensor, and this is a very fascinating work that was done with collaboration with a group in Cambridge. So we have the OACT right here. So this is the drain, this is the source. In blue, we have basically my polymer. And on the top of my polymer, what I do, I create, or not myself, the students at Cambridge, they actually they deposited epithelial cells. Epithelial cells is basically the cells that covers your stomach, our stomach, mammalian stomach. And basically what happened when you get food poisoning, which is, what is the name? Salmonella. When we eat some of this street food around here and you don't feel well, it's basically because you have eaten a salmonella. And salmonella, the way actually it interacts with you is by basically rupturing the tight junction between your cells of your epithelial cells. So you have different cells, one on the side of the other, and they actually have proteins to bind them together. And these proteins are called tight junction. And basically the salmonella used to eat that particular protein that actually holds the epithelial cell together. And by eating that protein, it opens up a way for all the acidic composition of your stomach to enter into your blood veins, and therefore you get some poison, food poisoning. It's not that the bacteria causes it. It's because what actually the bacteria eats causes a ways for other type of materials to interact with your bloodstream. It's very interesting. So what actually the Cambridge group did, they say, okay, let's put on the top of my polymer, on the top of the channel of that transistor, we are going to grow this epithelial cell. And basically what is going to happen when I apply a voltage, a gate voltage like this, and remember that here I have a series of epithelial cells, those ions will get blocked because, you know, when the epithelial cell is healthy, we have this tight juncture, so the ions cannot penetrate in. And if the ions cannot penetrate in, I'm not going to have any current in my drain source current. However, when we put, along with this transistor, some sort of milk or other type of food that has salmonella and leave that thing to develop for some time, the salmonella will basically eat the tight junction, which is holding those cells together. And after that, if I apply a gate voltage, ions will have an easy path to go into my polymer, and therefore I can sense whether or not those tight junctions are intact or not. It's very simple, but it's very, very impactful. And we actually did this. So in blue, it's basically without tight junction. So you see a little bit of charging of my capacitor, but it's very small. It's very, not only small, but very slow. But when we have the salmonella introduced to our device or sensor, you see that the charging change characteristic very fast. And by actually studying how this developed from this stage to that state over time, I can even build a model to back calculate how those membranes are actually being eaten by the salmonella and sort of understand a little bit of this biological process, which is, again, very important. And you can think about this, a OACT I can build in my lab for about 50 cents, something like that. It's very affordable. So you can think about incorporating all this biosensor in every, gallon of milk that you buy. And before buying, you just break it a little bit. You break some small little sealing that are added to this biosensor. Let the milk interact with your biosensor. And then you read it. If it becomes blue, you can buy it. If it becomes red, then you just waste it because there is salmonella. Very simple and would, not for São Paulo, but from poorer regions of Brazil and even outside Brazil, that could be a very good thing to be incorporated. Anyway, so you can do other things. You can actually use those materials for brain recording. Another group is doing the same thing. And of course, because polymers are flexible, you can also build, all those transistors on the top of PET substrate and do all kinds of, flexibility experiments, and they actually keep their function pretty much intact. So there is a lot of doing with this. So I think I have 10 minutes about it, right? 5 minutes. So I'm going to jump real quick to another application that I think it's interesting for us. This is a literature mapping that I did when I started my postdoc at Stanford, because I was entering a new field, so I didn't know what actually was the empty gap or the gaps in the literature. So I actually basically mapped the number of articles, varying from fundamentals, anything in between, and application. And basically, the big amount of articles were in application, as always. Biosensing, similar to the one I just showed it to you, was one of the top. A little bit of batteries. I forgot to translate this. Biointerface is basically those neural recordings. That actually is a very interesting vertical for a biomedical application. I'm not going to enter in details on that as well. And what I actually understood is there was very little on fundamentals, which is how is the case again, and no new or creative application. So I decided to focus on these two main verticals that actually were some sort of, were missing on that field of research. And, going into the fundamentals, we actually proposed a model that was actually very useful. I'm not going to go in details because of the time, but we basically were able to, reconstruct the transient current of AOACT, and was the first time a model we're able to fully reconstruct. We used, equivalent circuits and injecting physics, device physics, to basically build up the model. And here's, a experimental fitting of, two different measurements. As you see, they are very good. And this, we extended this modeling for biosensing, and we came up what we call a figure of merit to teach the bioelectronic community how to build highly sensitive biosensor. We noticed that, the biosensing community, we're basically building the worst transistors ever in order to sense particular phenomena. So we basically build up a figure of merit, and based on, device numbers, you can come and pick where you want to be, or what is the size you want to build your device in order to enhance operation or sensitivity of your device. I'm not going to go in details, but this generated a lot of articles. And the last application I want to show you is something related to artificial intelligence, which we call neuromorphic computing. You guys use more computer than I do, so you know that the Moore law is kind of getting into trouble right now. Basically, you are still able to, duplicate the number of transistors every, 1.5 years, basically. But if you look into the clock speed, this is basically tapering. We have a lot of problems, not only in terms of fabrication, but basically because of contact resistance. Is a problem, intrinsic problem in electronic. When you shrink, the resistivity of your contacts go up, and therefore they basically, more potential drops on that particular electrode, and therefore the device starts warming up faster. So it's a big problem. I'm not going into detail. So this is basically, acting against the increasing of the clock speed. So there is a lot of discussion to kind of build up new platforms for computing. You have, not only quantum computing, but we also have recently what they call brain-inspired computer. And there is a big project run by IBM and as well as Google to sort of come up with this platform, because this could be, not a hardware that would operate as an artificial intelligent hardware. Nowadays, all the efforts for artificial intelligence is basically on software. You have these deep learning softwares. It's basically a software problem. But you have to remember that those softwares are actually very robust. They are going to require faster computers. But we are not getting those computers as fast as we want. So basically, we want to look, a little bit more into the hardware as well, and come up with artificial intelligence that not only comprises softwares, but also comprises hardware. And this is what we did here. And the reason we want to look into the brain is because of this, of their parameters. So, you have a brain is basically a analog memory. But sorry.
What is artificial intelligence hardware?
Well, so it's a hardware that are capable to learn, right? So a deep learning software, it's somehow a software that processes a lot of data, right, and try to find ways to connect those padrões, how do I say? Patterns, yes. Connect patterns, and through those patterns, sort of learn somehow, right?
Okay, but when you say hardware, it seems that the machine somehow adjusts itself to...
Will learn, exactly. So this is closer. Yeah, I'm going to try to show you. It's used technology to bring plasticity to devices. It's actually something, ahead of our times. I completely understand. When we worked with this, we were kind of, oh, what is this? are we doing plasticity at all, or this is just an artifact? But I'm going to try to show you guys, a device that are capable to learn. At least you might have known about the Pavlov Dog, right? So it's a very first test for, conditioned intelligence. I'm going to explain you in a minute, and maybe I convince you that you can have an artificial inanimate device that are capable to some sort of learning mechanism, maybe. I'm going to show you in a minute.
Okay, so we understand, because I got a little bit confused with this, because we are building hardware that is specialized for artificial intelligence. Google has this tensor hardware that is super optimized and can get a little bit away with this scaling. So you're saying that that's not what you define as artificial intelligence.
Well,
like the brain, where the synapse itself will change.
Exactly.
And the conduction of electricity will depend on what you're doing.
Yeah, I think you're touching a very interesting point, because everything that is new is hard to be defined, right? If I ask you guys to define artificial intelligence, we are going to have 20 different definitions of artificial intelligence. So it's sort of this blurry concept where we are trying to learn what it is in a real matter. But in my sense, what I call artificial intelligence, or hardware that is capable to learn, is to use physics and engineering to propose a hardware that shows some properties of plasticity, plasticity is a learning by conditioning the device to learn some sort of activity. And I'm going to try to maybe convince you what is my understanding about artificial intelligence, and maybe we debate right after in the question, because I think I'm out of time. I'm going to jump a little bit here, and I want to discuss you a little bit about what motivated our work. So how the brain actually stores memory. And there is this model by Atkinson, which is called the multi-story model, which is one of the most accepted, some sort of model for memorization in our brain. And it's basically, memorization is basically on rehearsal, which is when you practice. That's the reason we have to, do exercise in physics to learn it. You have to practice. Otherwise, you don't memorize it. That's basically what the model says. So when you basically practice very few times, like blue, you sort of generate polarization or potentiation on the part of the brain you are stimulating. But because those are actually very spaced in time, that potentiation gets depleted very fast. And therefore, for your brain, that activity is not very important, and therefore the brain doesn't pay much attention to that particular activity. It's like me playing guitar. I like to play guitar, but I play guitar every once in 2 months. So my brain is not learning guitar at all, although I practice more than a year, right? But if I would practice every day, maybe I would be better at guitar as I am right now. So I'm playing guitar as blue, and therefore you basically have, what they call SM, which is sensory memorization, which is that memory that actually vanishes very fast, which is where I left my laser point, where is my water, something that is not very important. Or if you keep practicing, you transition to what they call STM, which is short-term memory. So it's memory that lasts maybe days. You go to a hotel, you remember the number of the hotel, because that is actually very important for you to come back home. But after 2 days, you get back to São Paulo, you completely forget the number of the room you were before, because it doesn't really matter. So that is what we call short-term memory. It could last days, but it will vanish eventually. But if you keep practicing, as in red, your brain, or that part of the brain, keeps actually firing, and firing is basically throwing ions outside of the neurons. And therefore, the potentiation strength of that area keep going on and on and on until a threshold where your brain understands that that activity is important. And then the brain somehow, and no one actually knows how they do it or how we do it, because we do it all the time, that particular activity becomes a habit. And then you can do that activity thinking about something else, like playing guitar and singing, playing guitar and thinking about the next physics test, or something like that. right? Now you play so much that became a habit, and then you can do other things. So this is basically, a very simple model of how your brain works. So we proposed a device which is basically a battery. So here I'm going to fly through because I know I'm actually extending, but I had a few questions, so give me more 2 minutes. So this is basically a device based on those materials that I just showed you. This is PB-TTT, but it's very similar to P3HT that I just presented to you. And this one is highly p-doped, so I have a lot of positive charge here, and here is neutral, right? So I put it a salt bridge. So if I connect these two electrodes, because this is highly doped, ions or charges, holes, will flow from one another until they equalize in charge. This is basically, one discharging in the other. So this is, you can think about this as a battery, basically. Battery works like this, right? So what we did, basically, was, using this battery structure, we just, in one of the electrodes, maybe, in this one, on the doped, instead of a full electrode to extract charges, we put it a channel, similar to a transistor. And why I want to put this channel? Because I want to keep measuring the conductivity between these two electrodes. And therefore, what I do, I can open, this anode to discharge, and ions or charges move to this electrode, and therefore less charges are in this material, right? And if I keep measuring the conductivity of this electrode as the charges are discharged, I'm going to see a change on conductivity on that particular electrode. And I can open and close because I can put a switch here, and I can open and close at different time, and therefore I'm going to reduce the conductivity. As I open that switch, the conductivity is maintained, so I have a new level of memory. If I shut that switch, charges will discharge, and then I move to a different level of memorization, that could be. And so I can build, basically an analog memory similar to this. So I open, so I move the stage of conductivity to a lower one. I open on the other way around because I can also apply a potential, so I move up or move down, and you see all those states are very volatile, so non-volatile, so they remain for a long time. So basically what I'm doing here, I'm actually walking at different potentiation on one of the electrodes by applying cycles of repeated either potential or open and close a switcher, like a switch of a light, right? And this could be related to a rehearsal because, for a computer, something, switching like a transistor could be something that would open and close a gate for discharging, and then I move to different levels of potentiation. So, with that device, what we wanted to do is basically replicate this multi-brain model, and what we did is basically open and close very different cycles, a number of cycles. Here is from 0 to 2,000. And you see that from 0 to less than 200, it stays more or less constant, which is basically the SEM memory. And as I go up, this starts changing conductivity. As you can see here, it starts going up, very similar to the model published by Atkins, and keeps going up with rehearsal at the point that actually gets to a taper or to the plateau level, which is basically the persistent memory. And of course, because this is a engineering machine, I can apply a reversal of rehearsing. So I can erase that memory, and therefore I can bring that memory down. So you can basically see that I could, using that structure, I could sort of replicate, the brain multi-memory model. And here's another data, but I want to move to this one. So we wanted to apply this to what we call plasticity, which is to see whether or not this particular device is able to learn. And the very first test for plasticity or conditioning learning is the Pavlov Dog. The Pavlov Dog works like this. You show a food to the dog, it salivates, right? Normal. Then you bell a ring, it doesn't salivate at all because it doesn't really understand what that means. But then what you do, number 3, which is fundamental for plasticity or learning by conditioning, you show the food and you ring the bell at the same time. And therefore, the dog will salivate, but will also, accomplish or connect the ring bell to the, plate of food. And therefore, on the next test, if you just ring a bell, it will salivate again, because now he comprehends that, ringing the bell would be associated to food. So this is what we call learning by conditioning, or conditioning something to learn. And animals learn like this. So normally you shake something and they come very quickly because they realize this is probably food, right? So what we did, we built, an electronic, very complicated one. And the important thing is you have to have some sort of connection between the sight of food and the hearing of the bell in order to create that plasticity. I'm not going into details because I'm actually ahead of time, but the way we actually did that in this circuit was using a relay. Relay is basically when I apply a potential between this point and the ground, the current on this coil will generate a magnetic field, which basically switch this circuit here, and therefore opens up the gate and change a resistivity of one of the electrodes. It's complicated. If you are very interested on understanding how this circuit works, come to me, I explain you afterward. I want to go even further, and there is 2 papers that we published on this. But basically, those are the results. So when you show the sight of food, which is basically an input signal on this synaptic circuit, you're going to have a current here, which means salivation. When you probe the bell ring, which is basically entering a potential on this terminal, which is the hearing potential, the resistivity here is very high that you are not going to measure any current on this end, and therefore the dog will not salivate. But when you actually enter with signal in both sight of food and bell ring, which is the test number 3, because this relay will close, you're going to have a discharge of one of the electrodes, and the resistivity will go down, and the sum of these 2 circuits will generate a current, and of course the dog will salivate. And then number 4, which is the real test, and after the relay is being shut, I enter with a signal as in the bell ring, and then because all this resistivity will go down, a current will go through this, and then I'm going to measure a salivation of the dog, even not having any sight of food. I'm glad to answer some questions or discuss even later, but I'm not want to waste your time again. We build also this as a flexible, because polymer can be flexible, but I'm going to finalize here my presentation, acknowledging my students. I'm missing 2 here, which is Richard and Tiago, and also the collaborators, Roshin Owens, Alberto Saleu, and Yakov Tufman, and of course all the agencies that actually supports that research. Thank you again, and sorry for the 10 minutes delay.
Question?
Sorry, I don't know if I understood correctly. Why do you need the device you showed in the Pavlov Dog? Where does it come in?
Yeah, so the device is right here. So basically the circuit, let me come back here. So the circuit is basically this, okay? So you have 2 entrances. So this is the site of food, the bell ring, and then you have 2 synaptic circuits. The synaptic circuits on the side of food is basically a resistor. And that could be because, I'm doing engineering, so it's not, a living system, so I can play with electronic. And therefore, if I apply any voltage here related to the ground, and the ground is here, of course, I'm going to have a current passing through this. And therefore, every time I put a sign of food signal, I'm going to have a salivation, right? So the synaptic circuit, number one, is basically a resistor to give me salivation. You know, this is no magic. This is, you know, engineering, so we have to play with this. And the synaptic number two is basically where my device enters. Here's the source and drain, and this is the gate. And basically what happens is when I polarize only the bell ring, I'm going to polarize this part as related to the ground, which is going to be this circuit, right? But this resistance between the drain and source is the one that I actually change by discharging or charging, right? So I can change this resistance from anywhere from 5 mega ohms to 0.5 kilo ohms or 500 ohms, right? So initially, my device is placed in a way that this is fully discharged, and therefore the resistivity of this channel is 5 mega ohms, right? So if I return to this point, here it's wrong. This is 5 mega ohms. So when I apply a potential here, I have 5 mega ohms in series. So my current here is going to be, you know, less than a microamp. So I'm not going to see anything. Just a spike because of the capacitive response, but nothing, right? However, when I apply both, you know, the bell ring and the site of food, what happened is the magic. And this is, again, electronics, right? It's not magic. It's just electronic. So when I polarize this, of course, I'm going to generate a current here through this circuit. That's bingo. It's going to generate a current here, no question asked. But I'm also going to polarize this point as related to ground, which is going to generate a current in my relay. And my relay will actually, because of the magnetic field, will close this circuit. And because I'm also applying a bell ring potential, this potential will polarize the gate. And therefore, I'm going to charge up this channel, and then I'm going to move my resistivity to 0.5 kilo ohms or 500 ohms. And now the conductivity of that channel changed abruptly or a lot in a way that in the next stage, which is simply polarize the bell ring, now this resistance is very small. It's no longer 5 mega ohm, and therefore I have a current here. This is what I call salivation. You know, this is a very simple, you know, electronic way to show Pavlov Dog, right? Of course, I play with time here to give me the result I want. I haven't mentioned time. But, you know, this is the first proposal, right? So people can take it and develop even further. You know, this can mimic, you know, here I learn in one step, in one rehearsal. And we know that brain doesn't learn in one rehearsal. It takes a lot of rehearsals. So, you know, this could be, he engineered to kind of mimic the multi-brain memory and start going towards a hardware that are capable to, you know, by applying different activities at the same time, rehearsing a lot of different times, will be capable to, you know, somehow learn by conditioning, you know. We don't know where this will bring, you know, it's a black box, you know, but it's a first proposal. People are looking into it, and we are one of these people doing this kind of debate as well.
Just like last question. So, but because of this bistability, would you call this device a memoristor?
Very close to, yeah, very close to, you know, a memoristor, but we call it a memory transistor because it's a transistor. But it's, yeah, that's. But there is a lot of advantage as compared to memoristor, because here, you know, we can play memoristor. There is a lot of different mechanisms, you know, breakups of the dielectrics, a lot of different, which is not, you cannot reverse. And here we can reverse. We can count one ion at a time, so we can do a way more stable and reversible device. But yeah, it could be classified as a memoristor, definitely.
So what's the capability of this device to readapt? Because one of the problems of both biological and artificial intelligence is that you can propose a different experiment that there is a switch, not a bell, and then you can get your lab rats hooked with food, and then you take away the food, or you make in a random basis, and then what happens is that he keeps doing the switch until he dies, even if there's no food. So if there's no, and you can do the same with artificial intelligence, you can hook in your training to do the wrong, and then circumstance changes and there's no readaptability. So if you keep ringing the bell and nothing happens anymore, can your switch go down and relearn that this is the pattern is gone?
Absolutely. You know, you have to always remember that this is electronics, right? So we can do all kinds of circuitry to do any type of different response we want. So we can talk, we can hire a electronic engineer and ask him, build up a memoristor that actually dies over, 10 rehearsals, right? And then by that particular circuit dying or being broken, it is going to activate a reverse signal that actually erases that memory. Yeah, I can see that happening. Of course, this circuit will get a little bit more complicated. And of course, we have to always remember that simplicity is important. So it's going to be a trade-off between, what is important and what is not important. But definitely, electronics are here, and you have all this rich amount of components like relays, transistor, batteries, capacitors, inductors that can do all these kind of tricks in electronics, and therefore it can be adapted to this. Because again, this is electronics, is not a living system. It's basically electronics. So we can definitely be very creative to play with all this kind of ideas, definitely.
Okay, let's thank Gregório again.
Thank you so much. There is some refreshments outside, I guess, right?